Hello, everyone. My name is Igor Lacroix. I'm a researcher at the Department of Mechanical and Mechatronics Engineering of the University of Brasília, under the supervision of Professor PhD Alberto José Álvares. And I will present you the algorithmic model in Grasshopper for the digital twinning of a Kuka KR70 R2100 robot. The model is a work in progress to be parameterized in many deposition options for a variety of parts being planar or non-planar. I will present you with the deposition process of a vase through laser metal deposition with wire technology. The robot is equipped with the Meltio tool for LMD-wire, and the setup is to contour the vase with a 3-bead layer of 1.2 millimeters height by 1 millimeters width for each bead. The vase prototype was modeled in rhinoceros, and we used the robot's add-on for Grasshopper, GH, to program the robot's movements. The GH model was organized in 3 parts. The 4 inputs, the Meltio tool, the Kuka robots, the part parameters, and the table and base parameters compose the left part of the model. The processing of the deposition paths and the targeting of the inputs to match the robot programming language happen in the center part of the model. Finally, in the right part are the 6 outputs of the robot's program: the code for simulation, the robot's movements, the Meltio tool's movements, the deposit material accordingly to the setup, and the depositing base and the support table. The first input is the Meltio tool, where the tool mesh is collected and introduced together with the specific wire length accordingly to the part contour properties. In Rhino, the tool mesh has to be placed at the origin of the Cartesian axis, so that the GH algorithm places it at the end of the robot. Let me show you this. So we place the Meltio tool mesh in the Cartesian origin, and the algorithm will place the tool in the end of the robot. The second input is the robot, where the corresponding mesh is retrieved together with metadata entered in the robot's add-on system by an XML file. This is the approximate path in the robot's add-on system where to place the 2 files: the Kuka robot meshes in a rhinoceros file, and the metadata XML file with information such as the definition of robot joints, speed, etc. The third input is the part parameters or the vase model in rhinoceros, together with the contour parameters. So we have the contour parameters here and the part parameters here. Meltio tool provides 3 standard bead types: a single contour with 0.6 millimeters height and 2 millimeters width, a double contour with 0.8 millimeters height and 1.5 millimeters width, and a triple contour that also applies to infill for solid parts with 1.2 millimeters height by 1 millimeter width. In Rhino, the vase mesh is placed in the Cartesian origin so that the robot can extrude it in the center of the base at the support table. So I'll show this again. We place the base geometry at the Cartesian origin. So that the robot can create the extrusion in the exact place on top of the base. The vase B-wrap is introduced in GH and a contour component is applied. The sequential offsets parameterize the contour accordingly to the previously mentioned specifications. In this example, the vase is sliced with planar sections. The fourth and last input is the base for extrusion, which provides the origin of the robot's movement placed in the support table. The algorithm collects the table mesh and, with its printing surface, models the appropriate base. With these four inputs, the GH model programs the operation of the robot in a two-step targeting process. First, it collects the parameters from the four inputs. The Meltio tool, which is connected here in the target. Speed and zone from the robot, which are also connected. Extrusion paths from the vase. So the contour, the two offsets for the triple contour are connected here so that they can program the planes for each contour and the selection in a sequence layer by layer. We finally connect the base surface for extrusion. The second target fine-tunes the first targeting with security parameters to avoid collisions and singularities during the deposition process, and connects to the robot program here, together with the home position of the robot and the Meltio tool. In the program components, we connect also the robot itself. Then the program is ready for simulation in Rhino. By clicking the playback button in the corresponding components, you can turn on the simulation. In the end, we have 6 outputs. The program results in a code for Kuka sync verification. And the simulation provides the robots and Meltio tools movements. A C# component generates the extrusions. And the table and base geometries are directly collected from the inputs. The speed of the simulation is controllable. In the end, the extruded object is prototyped. I would like to thank Professor Alberto Álvares for this opportunity to contribute to this research on the LMD-wire robotic cell. Also would like to thank Marco Maron for assisting in the GH programming, and Brian Figueroa and Lucas Araújo for their assistance during the simulation process. Thank you.